Hello folks, this is Dr. Young, and in this video we're going to talk about the Suzuki reaction, also known as the Suzuki-Miura or Miura reaction. And we're going to kind of cover what the basic components are, how we can make something with it, talk a little bit about why palladium is so special as a catalyst. So remember that for our organic class, we're just going to kind of do a brief overview of three reactions, We're going to briefly take a look at the Suzuki reaction, which was this top one. We're going to look at the Sonogashira, which was this one. And we're going to take a look at the olefin metathesis with the Grubbs catalyst, which is this one. So this video is all about how to connect two carbon groups using palladium and boronic acids or esters. So why palladium? Why is palladium so special, Because palladium is not cheap, It's one of the rare. It's a rare earth metal. It's not a rare earth metal. I shouldn't say that. It's a rarer metal, and it is found on this earth, but it's not one of the rare earth metals. It's not part of the F block. But it is very expensive, relatively speaking. And so we want to use it in small amounts, So it's important in catalysis. Or I should say it's important to use it as a catalyst, not as a stoichiometric reagent. But why palladium? Why not iron? Why not zinc or something like that? And it turns out it's all about palladium's electronegativity. It's all about the electronegativity. Which is a common theme throughout organic chemistry, or all of chemistry, So much is about this property of atoms called electronegativity, Just how much does an atom want electron density? How much does it pull on electron density? How stable is it once you have these negative charges? And so if you take a look at, for example, an old organolithium, So here's a organolithium. If you look at the electronegativity of carbon, you'll see that it's about 2.5. That's your electronegativity value. Let me get this out of the way here. The electronegativity of carbon is about 2.5, and the electronegativity of lithium is about 1. Whereas if you look down here at the one right below it, where we have our palladium, a carbon-palladium bond. You can call it organopalladium. Again, carbon is still 2.5, still carbon. But palladium's electronegativity is much closer to carbon's. It's 2.2. And so what's the consequence of that, We talked about before when we were looking at organometallic reagents like the organolithiums and the Grignards and stuff like that, that when you have a difference in electronegativity of, this delta E, this difference in electronegativity here is about 1.5, you're starting to get fairly ionic, Very polar. I'll put fairly ionic, or at the very least, we can say very polar. And what that means for us, what we saw for us with the organolithiums, is that makes them very strong bases, because you're building up a negative charge on a carbon, very strong bases, and good nucleophiles. That organolithium, that can be a nucleophile. So they become good nucleophiles. And so they do things like they react with carbonyls. Or in the case of the very strong base property of them, they react with acids. So you gotta kind of be careful, We said we had to protect alcohols that were around. Any carbonyl that is around will be attacked, and so you kind of want to be careful about what carbonyls are around. You might have to hide a carbonyl using an acetal or something like that. So we had to kind of be careful when we used our organolithiums, We had to be careful with the solvent. The solvent was a protic solvent. It would just get deprotonated, so you couldn't use organolithium in ethanol or something like that, because it just acid base and go away. But if we look at the organopalladiums, this stuff down here in purple, this is almost nonpolar, Your delta En, your difference in electronegativity here is only 0.3. So it's mostly nonpolar. It's almost nonpolar. So that means these things are not basic. They don't act as bases. And they're also not very nucleophilic. And so the big thing, so I'll put a couple stars here, is that they are much more tolerant of functional groups. So I'll say they're very functional group tolerant. Very functional group tolerant. We can do organometallic reactions. We can introduce palladium around carbonyls, around alcohols, all kinds of things. We don't have to worry about any side reactions. So palladium is really special in that regard. Nickel is also similar, but we're not doing a whole organometallic lecture here. We're just talking about the Suzuki reaction. But these palladium catalyzed cross couplings use palladium for this reason. It's much closer in electronegativity to carbon, and so it's much more nonpolar, and it's much less, you have to worry about fewer side reactions. So what is the Suzuki reaction? The idea is that it just involves the coupling of a molecule with a leaving group, a boronic acid, and you have to have palladium and a base. So the functional group with we got a leaving group here, so you have to have a molecule with a leaving group. So that's what I'm abbreviating right here. Right, we've got a leaving group, so Lg is supposed to be just really any leaving group. Right, so examples might be things like iodine or bromine or chlorine, etc. But it would also include some of the sulfonic acid or esters that we were talking about. So like things like triflates or tosylates, those work also. You got to kind of tweak conditions, but you can actually select for one of those leaving groups or another one. And the other key thing for us right now, because we're not doing a whole class on this again, is that we're going to stick with the examples that are sp hybridized or sp2 hybridized here. So not the ones that are sp3 hybridized. We're going to stick with they have to be sp2 or sp3. That's the most common Suzuki reaction. There are all kinds of tweaks and stuff you can do for sp3, but we're not going to go down that path yet. But we're going to stick with sp or sp2. So they have to have some kind of double bond or triple bond there. So that's the molecule with the leaving group. Now we're also going to have a molecule with a boronic acid or ester. The boronic acid piece, right, we're just saying that you're going to have an R group. It's going to be on a boron, and then the boronic acid is when you have two OHs here. So that'd be a boronic acid. A boronic ester would be if you had some R group, and again, that's just anything with a carbon on it. And then the ester means that you're going to have two ethers basically on it, two OR groups. And these R groups will be something different. Where the idea is that this is the thing that you're going to want to add on to whatever your molecule with the leaving group is, right? So that's what this molecule is. This is just saying that we're going to add some sort of R group here. We're going to put that R group on the thing that had our leaving group. We're going to couple those together, right? That's what they're cross-coupling. We're going to couple two things together that are not the same. And then we're going to have, right, palladium. So that's obvious since we're talking about palladium catalyzed cross-coupling. So here's palladium. Keep in mind, it's going to be not palladium metal. It's usually not palladium 0 for Suzuki's. It's usually palladium, well, it's introduced as a palladium 2. During the catalytic cycle, it's probably palladium 0, but again, that's not super important for us. But you're going to see this L2, right? And again, remember that this L is some sort of ligand. And these ligands are often phosphines. So you'll see P with some sort of R group. Those R groups can be methyls or phenyls or something like that. But most often these are phosphines. Right? These you might see phosphorus with 3 R groups. Now you may not have a very specific phosphine written there, but they should. There is some sort of ligand there. There's something there. And then the last piece here is that Suzuki reactions require a base to help with one of these steps in the catalytic cycle, the transmetallation. Again, don't worry about the catalytic cycle or the mechanism. That's for later chemistry for you in the future. Hopefully you'll take an organometallics chemistry class in the future. But you're going to have some sort of base, so I'm just leaving this generically as base. And this base can be anything from like good old sodium hydroxide to sodium carbonate or potassium phosphate, or even things like fluoride, KF, just something basic, something, weakly basic or even strongly basic. T-butoxide's used, just any kind of base. If you see a base, we're good. We throw it in there and we can do our Suzuki reaction. So if I look at this example down here, right below it, right here's a specific example without all the R's and stuff like that. It looks like, well, okay, here's my molecule with a leaving group, right? That is sp2 hybridized, check. That is bromine, that's good, that's a good leaving group. So it looks like I'm trying to take this whole piece And I'm going to try to attach it right to this piece. So in this case, I have the boronic acid, right, because it's OH, not OR. So it looks like I'm going to add a propyl piece. Do I have palladium? Yep, it's just left generically as palladium, PDL2, some generic ligand, nothing specific shown, that's fine. And then I've got sodium hydroxide, I've got my base, so that all checks out, we're good. And so to get the product, right, the idea is that we just take that whole piece that had the leaving group on it, and we just directly couple whatever the piece that was on the boronic acid or ester was. So since it was a propyl for us, I just slap a propyl in the exact place where the bromine was. And now I've made a new carbon-carbon bond, easy peasy, good yields, very straightforward. Didn't have to worry about that propyl attacking a carbonyl group or anything like that. I didn't have to worry about anything like that. So it's totally fine. Made a new carbon-carbon bond. Now let me show you another example. So same thing, right? I just have a new example down here. This substrate also still works because it's still sp2. I don't want you to think it has to be an aromatic ring. It doesn't. A lot of Suzuki reactions do occur on aromatic rings, but they don't have to. And so that means I'm going to take this thing and I'm going to attach exactly where the chlorine was. So I'm going to put right here, right? I need to add something here where I have that kind of squiggle. And that squiggle is not supposed to mean a mix of enantiomers. I just mean like that's where the new bond thing is going to be. And then I look over here to my reagents, and I do see a boronic ester in this case. So this would be an example of a boronic ester. These cyclic ones are not uncommon. They can be all kinds of different things. They can be really crazy looking cyclic things. All you want to look at is the alkyl group that's directly attached here. So I just see this. And I wanted to show you this example because I wanted to emphasize, well, another one of the nice things about these palladium catalyzed cross couplings is that you can get some really nice stereo selectivity. So in this case, this alkene, right, is in the trans shape. It's in the trans or the E, right? The groups are on opposite sides of that alkene. And it's going to maintain that stereochemistry. If it was trans there, it's still going to be trans on the other side, right? So here's my original piece with the chlorine, where the chlorine was. And you'll notice that when I coupled it to that new piece, it's still trans, right? It was trans there, and it's still trans there. And if it was cis to start off with, it would stay cis. It's not like things will relax to the trans or anything like that. They stay the same. So you're going to maintain any stereochemistry that you have at those points of attachment for like the alkenes, for example. And in this one, I'll just show, I just want to mention here that in this case, I didn't write PDL2, I wrote palladium chloride. That would be like kind of how we buy palladium often. It's one of the ways you can buy palladium. And then you're going to see the trimethylphosphine here. And that's fine. That's fine. If you see those, you should not be freaked out. You should just be like, oh, that's the same thing as like PDL2. We're all good. I'm just going to use that stuff. And then lastly, of course, here's your sodium carbonate, which is a totally fine base to use for Suzuki. So here's another example of being able to make a new carbon-carbon bond. In this example, hopefully you see that we haven't really had a good way to make a molecule like this one, this product. We haven't had a good way to bring two alkenes together that have very specific but different stereochemistries, right? And so that's one of the many ways that these palladium catalyzed cross couplings are very powerful. And the Suzuki is very powerful for that reason, is that I don't have to do 1,000 steps and then get a mixture of isomers and then clean up those isomers. I can just mix A plus B and it gives me exactly what I want, which again is why Suzuki and I think it was Negishi and Heck won that Nobel. So let's look at some examples. Here's a slew of examples. I think that you should pause and see what you can do with these. I've got boronic acids or esters. I've got the palladium stuff and some base stuff and something with a leaving group on it. You just need to connect one piece with the other piece and slap it together and call it good. So I'm going to let you pause here, see what you can do. The last one actually involves kind of an old reaction that you know, but maybe you don't remember that you knew, to make a boronic ester and then you do a Suzuki, but I'll stop talking. Go ahead and hit pause, see what you can do. Okay, so welcome back. Hopefully you took a crack at these. For this first one, right, it looks like I've got this aromatic thing. Yes, I've got a triflate and it's on an sp2 carbon, so that's all good. So I know I'm just taking this piece here and I need to connect. So I'm going to go ahead and draw that pyrimidine. La-di-da. I know that something's going to be here where that triflate was. And the thing that's going to be there, right, apparently is just a phenyl ring because I've got the phenylboronic acid here, palladium, I've got a base, and I'm doing Suzuki. So I'm just going to add the phenyl ring right there. And I've made a new aromatic ring, carbon bond. And again, for us, we didn't know a way to do that before. We never knew how to make a new carbon-carbon bond between two aromatic rings, but now the Suzuki allows us to. Right, where again, this is the green part, this is the blue part. The thing with the leaving group, the thing with the boronic acid. Now this one's a little different. This one's asking for the reagents here, right? So here we have the, we got a furan with an iodine on it. That must be the thing with the leaving group. Iodine's the good leaving group. And so the piece that I'm adding apparently is this alkene. So I just need to draw that alkene and then in that orientation, that correct orientation, right here we have a cis alkene. In that correct orientation, I just need to put a boronic acid. So I'm going to draw, to save myself the possibility of making a mistake, and for you all, I'm going to draw it in exactly the same orientation, right? So I've got those right carbons. I've got it in the same orientation. It's still cis, still Z. And you get to choose if you want to use the boronic acid or ester. Either one is fine. I will go with the ester. Why not? I'll pick O ethyl and O ethyl. Why not? It's going to be fine. And then I need the other things here, right? And I just remember that I need to remember that this is a palladium catalyzed cross coupling. So I'll put PD and I'll just leave it generic because why not? I will totally let you get away with putting something generic here. You don't have to put a specific phosphine. And then you just pick a base you want. I'm going to pick K3PO4 just to mix it up because a potassium phosphate's quite basic. That would work. And those would be good reagents for affecting that change, for doing that Suzuki reaction. The third one, we mix things up. I don't know how crazy you are about the color things, but I've been using green for the thing with the leaving group and blue for the thing that's the boronic ester or acid. So I'm going to try to continue that for you. Right, here's the piece that has the boronic ester. Apparently, here's the piece with the leaving group. So I just need to attach those two things together, right? So here's my phenyl ring with the methyl, where the bromine one is going to be my new thing. And again, this is another example where the alkene is cis, so I need to make sure that this alkene looks cis, and then make sure I've got enough carbons. And I'm going to double check because I kind of got a lot of carbons here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, I've got one too many carbons. This is why we check. So I'm going to erase this, la-di-da, and fix my work. Because it's really easy, right, when you connect two carbon pieces to lose track of things. So now I'm good. That's what the product should look like. And that's how I'm going to get a nice check. And then for the last one, you may remember taking alkenes or alkynes and adding BH3. And remember how they just kind of added to that alkene or alkyne? They did that sort of four-membered ring intermediate where they added to the syn addition, and it was anti-Markovnikov and all that stuff. That's what's going on in this first step. Only we don't have all the rest of the hydroboration stuff. So this is just how you put the boron on. So if I was to look at this reaction, the idea is that you have the H and the boron, and then in this case I have two O ethyls. And the mechanism is simply just that two electrons dump into that empty orbital on the boron, but at the same time it deposits the H. And so what I'd end up getting here, let's draw my cyclopentane. I have the alkene now, but there's an H here, and now there's a boron with two O ethyls on it. Right, that's what added. It was a syn addition, right? The H and the boron are on the same side. Again, this should remind you of the hydroboration. That's that syn addition. It's on the same side. Only I don't have as a step 2 peroxide and water and hydroxide. So it's not the whole hydroboration thing. Step 2 is, let's add phenyl bromide, palladium, and sodium hydroxide. So that's telling me that we're doing a Suzuki, right? This is how I made my boronic ester. Now I'm going to do Suzuki, apparently with phenyl bromide. So I'm just going to put a phenyl group here, right? So this is I made my boronic ester And now I'm going to put on the phenyl in that spot. So step 2 stuff is going to just give me this, where I put a phenyl where the boronic ester was. And that's how we do this. Now here's an example of a synthesis problem that, I could have given you for weeks, last term even maybe. Probably, yeah, I could have given it to you last term. Where I want to take benzene, I want to make this benzene with this alkene coming off of it. It's got a butenyl group on it, and it's specifically a cis or a Z. And I'm going to show you 2 ways to make it. One is an old way, and one is kind of a new way that we know how to do this, right? So I'm going to let you pause again. I'll stop talking for a sec. You see if you can turn our benzene into that. Go for it. So first, let me show you the old way. If we were all doing just aromatic chemistry, how you would have done this. Probably the easiest way would have been to take the acyl halide, so 1, 2, 3, 4, add your aluminum trichloride to make this friend. Right, so I can just acylate it. That's not a problem because I needed 4 carbons on there, so I'm thinking 4 carbons. Then, you could maybe reduce it with, say, sodium borohydride. To maybe turn that into an alcohol, right? 1, 2, 3, 4 carbons still. And then maybe you can do a dehydration. So let's say we add a bunch of phosphoric acid and we heat the bejesus out of it. Or you could have turned it into a chloride and you've done an E2 by adding like LDA or something like that. So I'll say that, and I'll put or also. Let's do this. Or SOCl2. And something like LDA would have worked also to give you an alkene, right? Do an E2 instead of a dehydration of an alcohol. But either way, from there, you'd have to add some halogens back to make a vicinal dibromide. And then done NaNH2 in at least 2 equivalents to make an alkyne. Right, to make that alkyne. And then once you have that alkyne, I could use H2 and that Lindlar's catalyst to get that specific cis alkene, right? To get the Z alkene, which is a lot of work, right? You can imagine this is a lot of work. I've got 1, 2, 3, 4, 5, 6, maybe 7 reactions if I go that purple route. So you got 6 or 7 reactions, even if they're all 90-something% yield, that adds up a lot. It takes up a lot of time. It's a lot of waste, right? If you think in atom economy and greenness, it's just a lot of work. It's kind of a pain. It's really kind of a pain. But that is a way that you could have made this molecule. Let's look at a new way using the Suzuki. What I could have done instead was simply done a bromination, right? Br2 and some catalyst. I'll do aluminum tribromide, or you could have done iron tribromide. Either one would have been fine. I'm getting excited, so I'm writing too fast. Br2, aluminum tribromide. Let's slap a bromine on there. And then all you got to do is just do a Suzuki. 2 steps, just do a Suzuki, right? So let's just say you have the boronic acid. And I'm going to slap that on the alkene I want. And I'm going to add palladium chloride and maybe potassium carbonate. And I'm going to pick a phosphine because I'm feeling fancy. I'm going to pick a trimethylphosphine or triphenylphosphine, or it doesn't matter. So I could do that same reaction, that same transformation in 2 steps. It would take me a fraction of the time. It'd be fewer columns, fewer recrystallizations, less characterization, less waste, etc., etc., etc. The only big downside is that you want to make sure that you can get this reagent, and palladium's a little expensive. So if we can recycle palladium or get cheap versions, which palladium chloride is relatively quote-unquote cheap, That's the only disadvantage of this route. But this route is so much faster. So you can imagine why you see so many palladium catalyzed cross couplings, or just organometallic reactions in general, I should say, in the manufacturing of pharmaceuticals and fine chemicals, is because it saves you time, and time is money. So I hope you have a greater appreciation for what the Suzuki reaction does, what it is and what it isn't. Definitely do some practice. We got practice problems in the book, and we got worksheets and everything. Look at your practice materials that I'm giving you. Study up. Let me know if you have any questions. Good luck.